Picture this, a row of 3 connected townhouses. Suddenly, the middle unit catches fire. So what actually stops the entire block from burning to the ground before the fire department even gets there? Well, a physical firewall, right? That heavy fire-resistant wall doesn't just magically make the fire disappear, but it contains it. It buys you time. It creates this crucial isolation from a dangerous event. And as we're going to see, that exact real-world physical need for isolation is literally the foundation where digital network security begins. Welcome to this explainer on cybersecurity architecture, specifically focusing on networks. Today, we're mapping out those invisible digital structures that keep our data safe. We're going to take these very tangible concepts of physical protection and apply them to the massive, complex webs of data that we all rely on every single day. Okay, let's dive into this. Here is our roadmap. First, we've got the basic security need. 2, firewall basics. 3, network strategies. And 4, security evolution. Part 1, security need, moving from the physical to the digital. Remember that townhouse fire we just talked about? Well, in a digital network, let's say you've got a user on a workstation trying to access a web server, which then talks to a database, we want to limit the spread of potential threats in exactly the same way. If a bad actor compromises that web server, we desperately need a digital firebreak so they can't just instantly burn down the database right behind it. By dropping digital firewalls between these different assets, we slow down the threats, we enforce the rules, and we basically give our security protocols the time and space they need to step in and neutralize the danger. In a business context, that extra time, it's the difference between a minor localized alert and a catastrophic, headline-making data breach. Moving right along to Part 2, Firewall Basics, Inspecting Traffic. Okay, so in its most basic form, a firewall performs what we call packet filtering. When data moves across a network, it moves in tiny little chunks called packets. Packet filtering basically just looks at the header of that data packet and checks a few specific things. The source address where it came from, the destination address where it's trying to go, and the port it wants to use. So, for example, if a user is just browsing the web, the firewall checks the packet and says, all right, port 80 or 443, that's standard web traffic, you're good to go. It filters out the bad and lets the expected traffic through based on a really strict set of rules. It's kind of the foundational, rigid gatekeeper of the whole network. And this brilliantly illustrates the evolution of how firewalls actually work. Basic packet filtering, it's just like looking at a mailing envelope. You check the to address and the return address, and if they look totally legitimate, you let it through. But you haven't actually looked inside. The next generation of security brought us stateful packet inspection. Now, this is like reading the open letter. It looks deep into the actual payload of the packet to see what data is really being sent. Plus, it looks at the context, meaning it actually remembers the previous packets you sent, and if you suddenly send something that breaks a logical sequence, boom, it stops you. It's a much deeper, smarter level of scrutiny. Another incredible tool in the firewall toolkit is the proxy. A proxy acts on behalf of something else. Instead of a user's workstation connecting directly end-to-end with a web server, a proxy server sits right in the middle. The user talks to the proxy, and the proxy turns around and talks to the web server. It intentionally breaks the connection right in half. Think of it like a really meticulous border customs agent. It gives us this perfect choke point to thoroughly inspect the traffic for viruses, enforce security policies, or even protect the privacy of the internal network before allowing any data to pass through. Then we have a technology that is just incredibly pervasive. In fact, it's very likely running in your own home right now. NAT, or Network Address Translation. NAT translates your hidden internal IP addresses into a single, internet-routable external address. This means you could literally have 100 different devices on your internal network, but to the outside world on the internet, they all look like they're coming from just one single IP address. It's basically the ultimate space saver that accidentally became one of our best security tools. So why does this matter so much for security? Well, it actually comes down to the number 10. By industry convention, any IP address starting with a 10, or really commonly 192.168 in home networks, is strictly non-routable across the open internet. If a malicious actor out there on the web tries to directly target your workstation's internal 10 dot address, the internet's routers will literally just drop the traffic. It goes absolutely nowhere. So NAT actually creates this amazing natural layer of protection where your internal traffic can easily get out through translation, but external attackers just cannot directly force their way inside. Let's move to Part 3, Network Strategies, and see how this all builds into massive network architectures. If we trace the historical timeline of network architecture, I gotta say it started out a bit recklessly. Back in the early internet days, people used a bastion host. They simply put their web server directly on the dangerous open internet just to keep it away from their internal network. It was basically the digital equivalent of leaving your front door wide open in the 90s. Highly exposed, definitely not recommended. Next came the tri-home setup, where a single firewall had 3 network cards to juggle internet traffic, web server traffic, and internal traffic all at once. Better, for sure, but it put all the pressure on one single point of failure. This naturally evolved into the modern gold standard, the DMZ. A DMZ, or demilitarized zone, is a designated buffer space. It completely separates the wild, untrusted internet on the outside from your highly trusted internal intranet on the inside. By using 2 separate firewalls, you create this perfectly contained middle ground where your internet-facing servers can sit safely. Honestly, the absolute easiest way to visualize a DMZ is using a traffic light. The external internet is the red zone, entirely untrusted, high danger. Your internal company network is the green zone, highly trusted. The DMZ in the middle is the yellow zone, an area of caution. Traffic from the red zone can enter the yellow zone to visit your web server, but those first-line firewalls absolutely block that red traffic from ever touching your green zone. So the absolutely crucial point here is that this architecture creates defense in depth. If you have a multi-tiered DMZ with multiple firewalls separating your web servers, your application servers, and your databases, you ensure there is never a single point of failure. If one firewall fails or gets bypassed somehow, the attacker is instantly met by a completely separate secondary firewall with its own strict rules. It's definitely more complex to manage, but it provides exponentially stronger security, which is exactly what stakeholders care about when they're evaluating risk. But wait, what happens when your internal trusted users need to travel out across that red, untrusted internet? That's exactly where VPNs, or virtual private networks, come in. A VPN establishes a highly secure, encrypted tunnel straight through the untrusted internet. It basically ensures cryptographic confidentiality, which renders any intercepted packets totally useless to bad actors. It's like having your own invisible pipe. Now, when deploying VPNs, there is a very distinct strategic choice to make: broad network versus app-specific. Older network layer protocols like IPsec are broad. They create a tunnel between 2 networks and just blindly encrypt absolutely everything flowing between them. It's simple, but it really lacks control. That's why modern security heavily favors app-specific protocols like SSH or TLS, the very protocol that gives you that little padlock icon in your web browser. App-specific VPNs encrypt data per application. This gives network administrators the granular control to individually manage, secure, or even completely shut down a specific service without taking the entire network offline. Finally, Part 4, Security Evolution, moving into the cloud. So what happens when we abandon physical boundaries entirely? Welcome to SASE, which stands for Secure Access Service Edge. As networks have completely decentralized and employees are working from pretty much everywhere, SASE represents this critical intersection where networking, security, and the cloud all beautifully merge into one holistic solution delivered directly at the edge. Now, what's really interesting about this slide is how we can break the SASE architecture down into a very simple equation. You just take your core network security components, add a software-defined WAN for real-time digital boundary agility, and then deliver it all from the cloud for massive elasticity. That entire combination, that is SASE. Think about the old days. In the past, if a company wanted a firewall, a secure web gateway, data loss prevention tools, and identity authentication, they had to go buy separate physical appliances. They had separate management consoles, and they required entirely different human administrators. SASE takes all of these disparate security functions, combines them logically, and delivers them dynamically right from the cloud to the user, no matter where in the world that user happens to be sitting. And this cloud-first evolution allows us to achieve something incredible: extreme microsegmentation. Instead of relying on these giant static DMZ zones, we can dynamically spin up tiny, highly controlled micronetworks around individual users and applications. We are basically shrinking the perimeter down to the absolute smallest possible size, vastly improving our agility to isolate threats. It is a total game changer. Which really leads us to our final thought. We started all this by building physical and digital walls to separate untrusted traffic from trusted internal networks. But with modern cloud architecture and this intense microsegmentation, we are rapidly approaching an era of zero trust. This is an architecture where we literally just assume a breach has already happened, and we grant trust to absolutely no one and no network by default. If the whole concept of a trusted internal network completely disappears, how does your data truly stay safe tomorrow? It's a pretty fascinating paradigm shift to think about. Thanks so much for joining this explainer, and keep questioning the architecture around you.